Here is the content. I will just briefly say what about is this presentation. At the first part, I will tell you some introduction about us and about the company. The second part is about sensitivity analysis. The third part, here just some brief description of the station, geological conditions and rock grouting test. Fourth part will be about the finite element models, which we done in MIDAS, GTS, and X. And the last slides will be about current state of construction work. So my name is Pavlina. I studied Faculty of Civil Engineering in Prague and in Stockholm. I have a 3 years experience as a geotechnical engineer, so I'm quite a junior designer, but everyone had to start. My colleague Martina also studied at Faculty of Civil Engineering. She already has a 16 years of experience as a structural engineer and nearly 10 years of experience with modeling in MIDAS, GTS, and X. We both work in Metro Project Praha. It's a consulting design and engineering company in Prague in Czech Republic. This year we have 50 years of anniversary because we were established in 1971, especially for the project of the first metro line in Prague. We do also other projects, for example, for transport constructions, as are metro, tram lines, railways, city road and highways, the underground structures, tunnels, barrier-free access to the stations. Also, we do bridges and civil engineering structures, architecture, technological equipment, building and traffic engineering. The company is based in Prague and has 200 employees. Some references what our company did and what design. Here is the map of Prague Metro network, and I will also use this map to somehow introduce my presentation. Actually, when you have a look at the map, there are yellow, red, and green line. These are the metro lines which are now in operation. The blue line is the planned metro line D, and if you find the point where is the intersection of the red line and the blue one in the suburb of the Prague, there is the Pankrac station, which about is this presentation. Here are some visualization of what we designed. For example, Prague metro line station Olbrachtova, or there is a photo of an extension of a Prague metro line from 2015. Other very nice projects are, for example, new railway connection Prague city center, Prague airport, Kladno, or the third metro line in Bulgaria in Sofia. Other very nice projects was high-speed railway terminal Prague East, Nehvězdy. So there are some visualizations what we done. The first part will be about the sensitivity analysis. Just briefly why we did it. It's because at the beginning of each finite element modeling, you should know how to set the mesh, which element type to choose or which shape function to use, so you can get the accurate results enough for you with some time which is it's okay for you. So I will start with a brief description of element types which are available in MIDAS, GTS, and X, and you can use for modeling. The really easy one are the scalar element with a single node. There are, for example, springs and dampers. One dimension of form element is linear and is defined by two nodes. We use them to model trusses, beam, or elastic links. two-dimensional form element has a shape of rectangle or triangle, and so it may consist from 3 to 4 nodes. The lines in between the edge nodes may be also curved, not just linear. There is a picture how the two-dimensional element looks like. And the last one are three-dimensional form element. They may have the shape of tetrahedron, pentahedron, or hexahedron, and are at this category solid elements are included. Actually, you have to also choose the order of the element and their shape function. So you can use 3-node triangle or 6-node triangle, which is much more accurate, but you need to have a look to the computational time, which is more demanding. And the same applies for a rectangle, where you can have a 4-noded or 8-noded rectangle. So here is the table which summarize the calculations which we perform to actually understand the element type, understand which size we should use or shape function. So we did 24 models with different mesh parameters, and we studied computational time and the accuracy of the results. At the right, you have the picture just to illustrate how the mesh looks like. So you may see that the hybrid quadratic with element size half to 5 meter is the finest one here. To compare this sensitivity analysis, to do the sensitivity analysis and compare this model, here are the graphs where in the right corner you can see vertical displacement for element of size from 2 to 10 meter, and at the bottom there is a stress for the element of the same size. That's for the different element size, so you can compare how behave different element types and their shape function, which are used for modeling. So you may see that at some points the displacement may be even 2 times higher for hybrid quadratic elements than for the tetralinear elements. Here are the displacements for tetralinear elements with different element size. Also, it has an effect, and you should choose quite properly which element size you will use. As you use the element with a higher order, actually the lines are really close to each other, and the range of the displacement, the results, is smaller. So there is not such a huge impact to the results if you use the higher order elements. And here is the summary where in one graph you may see all 24 calculations and how it behaves, how was the vertical displacement at one particular point of the model. And it's evident that it's very important to know how it behaves and which elements you use, so you can say how accurate your model and your results are. When you compare computational time, which is very important, together with vertical displacement, you see that really accurate results are very time demanding. And at this time, you have to decide which element type you will use. For modeling of a Pankrac station, we use tetralinear elements with element size 1 to 10 meter. Even if it's not so accurate, you know how it behaves, how the displacements are occurred, and for us at that time was very important to shorten the computational time as much as possible. Let's move to the section 3. I will tell you some brief introduction of the metro station Pankrac on line D. Here is the map of Prague metro lines again. So again, Pankrac station you may find in the intersection of metro line C and the blue line, which is metro line D. So actually, Pankrac station is a station which connects two lines, which is a transfer station. And here it's in detail. The red area is a Pankrac station on line C, which is already existing. It's there, it's in operation. The gray area below is a planned new Pankrac station on line D, so I will call it Pankrac T. Pankrac station D has 3 exits. In the northern part, there is one exit to Gemini office building, and in the southern part, there are 2 exits, one to Arkady shopping mall and the second one to the Budjovická street. Also, there is a direct connection to the existing metro line C. Pankrac station is designed as a mined, one-bound station with a side platforms. It's situated 33 meters below the ground and in the southern part just 4 meters below existing line C, so it's really close to the existing station. Here are some visualization from the interior of the Pankrac station. And here the view to the old station. The northern part, there is the exit to Gemini, and the southern part, there are 2 exits and transfer to line C. And here we are really near to the existing line C. Here are some drawings just to have an idea about how it looks like there as the plan view of a platform level with exits in the southern part. And here the longitudinal section of the station tunnel on the left, or here above you may see metro line C. Some words about geology. That's the longitudinal section of a station with geology on the left. That's the northern part of the station. Here you may find the Silurian formations. Actually, we call them Kopanina and Litane formation. On the right side is the southern part of the station. That's the Ordovician formations, which we named Kosov formation. These 2 quasi-homogeneous units are divided by inclined layer of diabase, which are here in the middle marked with red lines, with red inclined lines. For you to have an idea about how the quality of rock is, I will show you the photos of a borehole J179. Here is the picture of the core of a borehole 179, and where at the top there is a fill. If you go deeper, there is quite nice borehole core of diabase. When we continue deeper, it's become quite bad. There is the geology like really difficult for excavation. The borehole core is not with very high quality, and these are the Kosov formations. To actually be able to do the excavation in a Kosov formation and do the southern part of the station, which is really complicated, we decided in advance to do the rock grouting test to see if we are able to improve the quality of the rock the stability of the rock mass, and the geotechnical parameters of the bedrock, so we can do the safe excavation. So rock grouting test consists from 2 boreholes. For the first time, we drilled borehole J257, in where we did 2 pressure meter tests to actually measure deformation modulus of a Kosov formation for natural geotechnical conditions. In the second borehole, we did the rock grouting test, and after that we performed 6 pressure meter tests to measure this modulus for a grouted rock. We used for rock grouting 2 types of chemical grouts, 1 component PU resin and 2 component PU resin, just to see how it behaves and which one will be better for this case. Here's the report from a rock grouting test. And here's some pictures from a rock grouting, where in the right corner you may see the foam which create the PU resin. And here is a borehole already after rock grouting. And here is the detail, where you may see the PU resin in a really fine crack of Kosov formation. So as I already said, we did the series of a 6 pressure meter test to evaluate modulus of deformation. You can compare the value of modulus of deformation in this table, that for example in a depth of 18.7 for natural geological conditions it was 190 megapascals, and after the grouting in the same depth we have 385 megapascals. So yes, it improves quite a lot, but when you have a look to the values, and the range of the value is quite wide, so to do the finite element modeling with 1 rock grouting test is not so easy. So to cover the problem that the rock grouting is affected by many things like type of a grout, quality of work, water level, and so on, we actually decided to do the design on actually 20 different inputs data. So we use statistical method called Latin hype cube sampling to generate 20 different geotechnical data for a grouted Kosov formation, and we performed analysis to see how big is the effect or impact of a rock grouting to the behavior of a rock mass during the excavation. Here are the parameters which were like the result of the Latin high cube sampling, and these parameters afterwards we used for models of a Pankrac station. So section 4, so let's move actually to the finite element modeling of Pankrac station in MIDAS, GTS, and X. I will start with 3D geology. This is a simplified geological model which is based on a geological investigation and geological map of the capital of Prague. You may see there the inclined layers of the airbase. There are also the low quality Kosov formation and the Litany and Kopanina formation. You may see there metro line C, and below it there is a Pankrac station D. And because this model is really big, we decided for the initial or preliminary design to study just the southern part, where is the worst geology, where we are really near by the existing line C, and where the excavation of the Pankrac station is really complicated. To be able to shorten the computational time, as I said, it was very important for us. We divided this southern part of the station into three models, A, B, and C. So it was easier for us to calculate it. Model A we call geological investigation. It consists from access shaft, access edit, and a pilot tunnel. Here is the pilot tunnel of a future station Pankrac D. Here above are the existing tunnels of line C. In Model B, we studied excavation of the Pankrac station. It's excavated by the sequences. And Model C, where we did the excavation of a bench and invert. So actually to complete the excavation from Model A, that's the future transfer hole. Here are the inputs for Model A, geological investigation. And actually, we performed for each model, for example, for Model A, the zero calculation, where we studied behavior of a rock mass for the natural geological conditions, and after that 20 calculations, and for actually the inputs which we generated from the Latin Hypercube sampling method. The same inputs are actually for B, and for Model C they are all the time the same. When I summarize this calculation, all models, all 63 models which we perform took us 44 days, and the file size is bigger than 4,000 gigabytes. So it's so now I may go back to sensitivity and activity analysis, and to say that it's very important to choose the correct mesh settings. Now I will tell you something about each model. I will start with Model A. Here you may see the cross section of the vertical access shaft. It's from second pile voil with pile diameter of 1 meter. It has a total depth of 30 meters. Here is the other part, is excavation of the access edit in a total length of 25 meters. The third part is excavation of the pilot tunnel with a length of 91 meters. All parts has a primary lining from a reinforced concrete. Here in the fourth step, we model row grouting, which is in a cross section. You may nicely see where we try to improve the geotechnical parameters of a rock mass, and just quite near here above are the existing metro line C. Here are the rock grouting and how we actually model this in MIDAS. What we did is that we changed the property of a selected elements which were in a range of the area where the rock grouting was applied or was expected that will be applied. And the fifth part, that's the excavation of the second half of top heading of the pilot tunnel. The last part of the Model A is the excavation of the pilot tunnel at the bottom of the Pankrac station. Its complete length is 60 meters. as a cross section, and you may see that it's the part of the future station tunnel. Some info about model in MIDAS. There is a size of the model 150 to 250 and 100 in height. Number of elements were more than 400,000. As I already said, we use tetralinear elements with element size 1 to 10 meters. For a material model, we always use more column modified, and model A had 305 construction stages. And here I will just jump into MIDAS. I hope. Yes. So here is the model A, the model of geological investigation. And as you may see, there's the access shaft, access edit, and the pilot tunnel. And quite near above are the existing tunnels of the metro line C. I may show you just quickly how we model rock grounding, as it's already said that at a particular stage, we just choose the material property of a selected elements in the area of actually grouted rock. If I would like to link actually the model A with the reality, now the geotechnical investigation was finished. Here is the photo of the access shaft. Here's the photo of access edit. And here's the pilot tunnel, the left side of the pilot tunnel. Here's the pilot tunnel after rock grouting, so you may see how many boreholes was done to actually properly grouted the rock mass. And here is excavated also the right part of the top heading part of the future transfer hole. Here is a detail of rock grouting. Here you may see the tiny white or yellow lines of PU resin in fine cracks of a Kosov formation. When we compare what was expected in Model A, what was actual consumption, so for example, the consumption of grout was about 30% less than was expected, but on the other hand, volume of grouted rock was nearly 4 times higher, or even more than 4 times higher. Model B in the first stage, we actually cast the concrete to the part of the pilot tunnel from a Model A to do the safe excavation of the station further. Second step was to do the rock grouting from the pilot tunnel from Model A to be able to afterwards safely do the excavation of the station. Here it's again elements with changed material property. So the excavation of its own station was done by sequences, and it started with a left top heading part, and it continues with a right top heading part, and it was followed by the excavation of the left bench and invert, and after that also the right bench and invert. Last step from excavation was to drill out the middle top heading part. And after we knocked down the inner walls of primary lining, we actually had the complete excavation profile of 350 square meters, and the primary lining thickness was there about 500 millimeters. Here's the view from the MIDAS on the sequenced face of a station tunnel. Some info about model B from MIDAS. The size of the model is same. It has 600,000 elements, and number of construction stages is 327. Other parameters are the same for model A, B, and C. Yes, and here again, I will try to, oh, sorry. As a stop note, to show you actually model B. Yes, it's here. So you may see nicely the sequence phase of a station tunnel. Again, metro line above. Here the wired one is a more part from model A, which is we just put here so we can shorten the computational time, because the analysis of a model A is not here but in a model A. So it just put inside this model. I will go back to my presentation. Here is model C, the last one, to model whole Pankrac station. At the first step, we have to demolish the concrete which was casted in model B to the left side of the pilot tunnel. After that, the remaining parts from model A over a top heading part of the future transfer hole were excavated in next stages, and as in a third step we did the excavation of a bench of a transfer hole, and the last step was to excavate the invert of the transfer hole. So now we have the complete profile of the future transfer hole, which is 174 square meters. Here is just the model or the picture from the MIDAS. Here is the station tunnel, and this is the transfer hole from model C. Here's some information about model again. This model has 70 construction stages and 470,000 elements. And again, that's the animation of a construction stage. But I would like to jump again to the MIDAS to show you the model there. You may see it here together with model A, the wired one. The green one is model B, the excavation of the station tunnel, and the model C, it is modeled step by step, sequence by stage by stage, and it's the future transfer hole. Here are the results actually from model A, and the vertical displacement set. On the left, there are always results for natural geoconditions, and on the right, there's the results for rock grouting. So you may compare the effect of rock grouting to the behavior or displacement and settlement of line C to the natural geotechnical conditions. And for example, here we may quite nicely compare that for model A, in case of natural geological conditions, the displacement in the point of arrow was 12 millimeters, but for the rock grouting, just 6. So it's a half. And here is the displacement of the existing tunnels of metro line C. Then again, for natural geoconditions, there was not the displacement, the settlement of this metro line 7 millimeters, but after the rock grouting, just 5.6. Here are the results of stress in a rock mass in the direction Z, again for natural geoconditions and rock grouting. Here is, for example, model B and its vertical displacement Z again. So you may again compare the effect of rock grouting. For example, here, the vertical displacement at the top of the wall of the station tunnel was for natural geoconditions 16 millimeters, but for rock grouting, or after the rock grouting was applied, just 9. Here again, it's quite nicely seen the effect of rock grouting and how the displacement was minimized. And here are the vertical displacement Z for existing tunnels of line C. Here are the stresses in rock mass for model B. Here is, for example, the cross section of the station with tunnels of line C above. And here's the model C. And again, vertical displacement for model C and for 2 conditions. So here, for example, you may see the maximum deformation for natural geocondition and for rock grouting. And if we compare the actual values at the point of the top of the transfer hole, the top of the vault, here we have 23 millimeters for natural geoconditions, and after rock grouting, after just 9 millimeters. And stress in a rock mass for model C. That's the longitudinal section of a station tunnel with already excavated connection to the transfer hole. To be able to evaluate 63 models together, which were divided into 3 submodels, we choose 5 points. 3 points are placed on the lining of the station, 2 points are placed on the tunnel of line C. At these 5 points, we apply the method of superposition, so we actually sum up the displacement from model A, B, and C together to get the complete or total vertical displacement in a direction Z. So if you imagine the first 300 stages are from model A, second 300 stages are from model B, and last 70 stages are from model C. And here you may see, or to compare, the reference value or the reference displacement for natural geological conditions with expected value after the rock grouting. This expected value is the result of a statistical evaluation of all 63 models, and the statistical evaluation was done together with Technical University in Ostrava and with Mrs. Rubeshova. The same thing, the superposition method, we also apply to the point 2, 3, 4, and 5. So you may compare the effect if the rock grouting was applied and if not. So it's and here is the settlement of the existing line C, which is caused by excavation of the station Pankrac T. And point 5. To sum up these finite element models, here in the table in a yellow row you may see the reference value, actually vertical displacement for 0.125 for case of natural geological conditions. If a rock grouted was applied and the improvement of a bedrock was done, there is you may see the results in a green row, and it's seen that the difference is really big, and it's very important for this to use the rock grouting. When we compare our results with a norm of 73.10.01, there is a table where the limiting values of settlement and differential settlement are stated. So for total settlement of a reinforced concrete structure, which is the most closest one to the tunnels, is set just 60 millimeters. For differential settlement, after that 0.002. When we compare this allowed maximum value of settlement and differential settlement and compare it to our results, you may see that the settlement of Metroline C for the natural geological conditions and for conditions of rock grouting are above the limiting value. But on the other hand, when you compare differential settlement of Metro tunnel line C, this in case of natural geological conditions, it exceeds the limiting value. So the rock grouting in this case is really necessary. So based on the finite element modeling on our preliminary design and working with different type of rock grouts and different geotechnical parameters of a grouted rock mass, we may see that the rock grouting is not just the necessary, but it's a must for to use the safe or to do the safe and successful excavation over such a huge project as the station of a Pankrac D. In the last section of this presentation, I would like to say some words about current state of construction work on Metro Line D. As I already said, in 2019, the geotechnical investigation, it's actually our model A. The investigation, the works there started this summer, 2021. The geotechnical investigation was finished, and now we are waiting for a complete geotechnical report from these works. We hope we will get this report in a few months. Nowadays was decided to continue with geotechnical investigation. So now the excavation works on a bench and invert are in progress. So you may see this on a pictures here, where the excavation of bench and invert is done right now. And here. Nowadays, the construction of Metro Line C is waiting for a rightful building permit, and we hope that it will continue soon, because for us it means another really interesting work with MIDAS, and I'm quite looking forward to it. Last few words I would like to say something about why we choose MIDAS GTS-NX for modeling of Pankrac Station D. It's mainly about its really complex geotechnical software. You may use it to design foundations, but also the underground stations, sheet pile walls, and many other geotechnical issues. Also, it's very good for calculation. It has quite short computational time. Mesh setting I also really like, because you can define everything what you want. It has an extensive element library. You can choose shape functions and actual shape of the element. Actually, for the other design procedure of Pankrac T in MIDAS, we are going to do the full coupled stress seepage analysis, and to also apply the water flow to the model, because it's really important for us. So I think the MIDAS is really powerful tool for 3D numerical modeling of complex geotechnical design, and we may recommend it. I hope you enjoyed this presentation, and thank you for listening.